So, dear guests, ladies and gentlemen, welcome to this afternoon breakout session where we want to bring together our conference topic, water reuse and applied digitalization. My name is Richard Festner. I'm working in Munich for Bentley Systems, being globally responsible for software development enabling smart city digital twins. And the digital twin approach is specifically what we want to hear about and discuss in the next 45 minutes against the background of a current research project. And by this, try to answer the question, can water reuse benefit from digital twinning? So what makes this so exciting is the fact that in the context of digital technologies, everybody is talking about digital twins today, right? And as was the case with computer-aided design 40 years ago, or building information modeling almost 20 years ago, digital twins are now reshaping how infrastructure is designed, constructed, and operated. And we owe in large part to the Industry 4.0 approach with cyber-physical systems that digital twinning is so prominent. So what is a digital twin? A digital twin is a realistic and dynamic digital representation of a physical asset, process, or system in the built or natural environment. It connects the physical and the digital worlds, where the digital one dynamically reflects changes in the physical. It provides improved visualization, analytics, and simulation capabilities for data-driven decisions. And anytime, anywhere, you can view, monitor, and gather insights to improve efficiency, reliability, and sustainability. What distinguishes a digital twin from any other digital model is its connection to the physical asset. A bidirectional data flow between the physical asset and the digital twin, actually a data cycle, enables insights and creates opportunities for interventions in the physical asset. If this is not established, it's more accurate to speak about a digital shadow. That said, the concept of digital twins is not new, but the infrastructure sector, including water, are lagging behind, and we still need to gain more experience with pilot projects. Now, FlexStreet is such a project. And I'm pleased to introduce two colleagues who will present such a cyber-physical water system, referring to this multi-year research project. We have Dr. Ulf Miehe with us. He's head of process innovation team at the Berlin Center of Competence for Water. And he has been conducting various national and European research projects in the field of advanced wastewater treatment and water reuse. He's the chairman of the working group on ozonation at the German Water and Wastewater Association. And second, we have Dr. Achim Ried with us. He's chief engineer, disinfection and oxidation with Xylem. His business activities and research interests are in the fields of water and wastewater treatment and water reuse. He was involved as partner in several national and international research projects over the last 25 years. And one area of focus is the optimization of multi-barrier solutions by generating synergies between process technologies, including advanced monitoring and control concepts. I will let both present their slides before we enter into the Q&As, because Ulf is presenting more of the physical plant to process, whereas Achim is more going into the digital twin side of the system. And it's good to have the full picture before we start discussing. Anyway, just please use the chat function here in this Zoom meeting for questions or comments, and I'll pick them up later. With that, Ulf, the stage is yours. You can start presenting. Thanks a lot.
Okay. So now you should see it. Oh, this took quite a while. So thanks for the kind introduction, Mr. Festner. Well, you already introduced the project FlexStreet. So FlexStreet is one of those already mentioned water reuse project funded by the German Ministry for Education and Research. It's a rather large consortium which is coordinated by Aachen University by Professor Windgens. And then within this group, there's one topic which is also focusing on digital twinning. So that's one part of the project, not the whole project is about digital twinning. The whole project is more about water reuse and agriculture and the related quality challenges, let's say, and technologies, how to overcome them. The project basically builds on two main drivers. So on the one hand, on a national level, we see a strong driver regarding protecting the aquatic ecosystems from chemicals like pharmaceuticals, household chemicals, industrial chemicals. So a lot has been done in the last 10, 15 years in this field. We already see full-scale installations by ozonation, activated carbon, powdered activated carbon. And what we think is, okay, now let's move one step further. If you already go for advanced treatment for surface water protection, why not making use or combining this with the EU approach on water reuse, with a new regulation on minimum water quality demands in agricultural reuse? And well, there we are. This is FlexStreet, where we look on different technology combinations, which always wants to fulfill, on the one hand, the chemical removal to protect soil ecosystems, to avoid the transfer of micropollutants to the crop, but also to allow surface water protection when we do not need water reuse. Well, so here we focus at a pilot plant which is located in Brunswick, like Braunschweig. So you already know the Abwasserverband Braunschweig, so they're also part of this project. So basically it's set up of an ozonation unit to remove chemicals, then a filtration unit, which is a post-treatment after the ozonation. So ozonation should always be followed by a biological post-treatment, and then a UV disinfection to really get very low with the microbial contamination. Of course, we do not start from zero. So we have been researching ozonation for a lot of years now. But first, let's have a look on the quality targets we want to achieve. And now it becomes interesting. This is also a bit like what our digital twin should do. So on the one hand, we have targets for the ozonation to remove a certain list of chemicals by more than 80%. But this is a compliance level on an annual average. We want to bring down the turbidity to lower than 1 milligram per liter to be controlled online. And then the EU directive asked for below 10 E. coli per 100 milliliter if you want to do unrestricted irrigation. And here the compliance level is weekly sampling 90% of the samples. And this is basically the field of play where we want to use our digital twin, how to simultaneously control these three targets without boosting energy consumption or cost. So if we have a look a bit like on the background, of course, we will build on, let's say, proven concepts for controlling such plants like ozonation. Just measure the UV absorbance in the water before and after ozonation. And the more you reduce the UV absorbance, the more delta UVA you have, the more trace organic removal you will have. You can see this here in this graph for two typical compounds. Benzotriazole is a corrosion inhibitor, and valsartanic acid is a metabolite of a pharmaceutical. So you see here from different pilot plants or lab scale experiments, the higher your delta UV is, the higher your pharmaceutical removal is. So that's easy. If we apply the same concept for disinfection. So what you see here now is the E. coli concentration in yellow in different secondary effluents, and then in blue after ozonation. So, and here what you can see, it also follows a similar trend, but don't be fooled. So this is a log scale unit. So in reality, of course, you have like a factor more than 100 between those data points. What you see also here on the right hand is a bit like, okay, these are the water quality classes in the EU regulation. So we come from D, C, B, A, and A. This is where we want to go. So in red, now you see this is a typical operational window for pharmaceutical removal. It's clearly see this is impossible to go for class A water quality. And this is also the reason why we need a multi-barrier approach. You cannot achieve water class A by direct ozonation. That's why we need a second step of UV disinfection. One aspect which also should be part of a digital twin is quality control. We need a lot of surrogate parameters like UVA, turbidity, we will have temperature also included. And especially if you go for things like UVA, digital twin sounds easy, and sometimes well, the one main difficulty is really the online sensors. So this is also something we need to look in. We have several years of experience with such sensors now, and they're cleaning. So that's an aspect we also want to include in the digital twin. Well, and before I hand over to Achim, this is basically then the overall concept. On the right hand, you see how it really looks in reality. So it's not a lab scale unit, it's a rather large pilot plant. We have the ozonation, filtration, UV disinfection. Each of them has, of course, a physical PLC, or in case, for example, of the ozonation, this is a Siemens S7, so classic, let's say, industrial standard. And then this will be backed up by a virtual control in which we can model like the individual steps, but also the whole process together. We will feed, of course, the offline water quality data into it, because like if we want to train the system, we need like the offline data on microbial quality from pharmaceuticals and so on. And so on, this will be then all merged together. That's basically how it will look like. And now I will hand over to Achim, who will explain a bit more in detail how this will be done. So thanks, that's all from my side.
Okay, perfect. Also, let's see. Now I can't share the screen. Okay, Now I think it should work.
Good.
Okay, perfect. Ulf, thanks again a lot for taking the part one. Now I'm continuing with the part two of that. And before I step into a bit more discussion about the digital twins itself, I would like to summarize a bit the needs, because these are, I think, important step one, to think about which specific needs should be satisfied or solved by a digital twin, right? And we just heard by Ulf that with going on these wastewater reuse scenarios, the existing wastewater treatment plant probably will need to be upgraded by additional treatment solutions. So the need is there then definitely to manage and operate new treatment, additional treatment equipment at the wastewater treatment plant. So the plant manager and operator has to take care of new equipment, maybe also new regulations, new targets, as we just heard already. So the need is here to achieve these requested targets with additional equipment. And we also heard already that this is a multi-barrier system, which means that there is several treatment steps combined, which increases then for the operator and the manager the duty to balance that all out, to understand the synergies between the treatment steps and to manage and operate that in the most optimized way. And we heard already about needs about so-called visual sensors, surrogate sensors, and specifically here for UV disinfection performance. And in general, I think there is also a need to capture knowledge, to build up knowledge, operational knowledge, how to operate and run the plant. And that could be also a topic to think about how digital twin could help here. And Richard already summarized a bit from the digital twin, but just to repeat one of them, because what is a digital twin and how they can benefit here? And as already mentioned, the digital twin is a virtual representative of the process. We are talking here about looking at our process here. So we have a mirror, a virtual mirror, and what that would allow us to play with a virtual plant in parallel to the physical real plant. That would allow us to simulate in real-time process conditions and run some so-called what-if scenarios. Yeah, you could play then with what will happen when, if, and this is then a kind of decision support system you can play around with the virtual plant before implementing it in the real-time operation. And if we think further by adding then so-called machine learning software elements that digital twin can learn and have self-learning and build up knowledge over time, which really then can cover this topic of how to secure operational knowledge and make available knowledge for operators and managers. And the ultimate goal here is then the autonomous operation, and that we will see, and we will test at the end how that can be done. Okay, let's move to the digital twin itself. So digital twin is not really new, so that's already known. And also these are known and practiced so far in the past years for municipal wastewater treatment plants. So there are examples out in practice where digital twins are implemented for example, optimizing biological processes. And important here, that's in general, but also for our project here, is that the data sources. So the digital twin needs the right input. Without the right input data, the digital twin can't work well. So we have to check out the availability of data like sensor data or data from the SCADA system, from the real life plant, and best would be, in any case, if there is historical data available from a plant to train the digital twin. And that is done in practice for biological treatment systems. Here's one example on the screen where digital twin is implemented at a biological treatment plant, wastewater treatment plant. And you can see here, the trained digital twin is predicting the nitrogen elimination rate. And the blue line is the prediction by the trained digital twin. And the white line is the actual system performance. And you can see with the trained twin that predicts that quite well. And that offers then the door to run and operate the plant with the digital twin to have the optimized operation windows. And for in example, the most energy consumption, or one of the key energy consumer at the biological treatment plant, is the aeration equipment. And here with an optimized operation, that in this case, the plant could up to 30% reducing the energy used for aeration. So there are some examples out where digital twin used already. And now we are back to our system here, as Ulf explained. So that is a new treatment train, additional treatment train. So there we need to collect information on that process to build up the digital twin. And I would like to mention here that one important starting point is that we need to, and what we did, to describe very seriously the existing plant, the existing data set, the data list, the data points which are available from the existing PLCs, from the physical plant, and also understand which lab data, other sensor data, what are the data sources available. And these overall data lists need to be understood from the modelers who are building up the virtual plant, the virtual PLC. And in addition, we have to make sure we have to build up a setup that these data transfer and data connectivity between the virtual plant and the physical plant are in place and that they can continuously exchange data, and you can then enable the system to match, learn, and calibrate over time. And this is the setup we will have in Braunschweig. And here I would like to mention the two experts. We have two partners here being experts in digital twinning. And on the one hand side, this is the company Pegasus, and on the other side, it is Aquatune, Xylem brand. And together with the combination of this expert knowledge, we are building up the modeling and the programming of the digital twin. And again, here, important is we do see here the master PLC of the physical plant, and then we do see the PLC connecting modules to the virtual world. And really important is here, and that was my observation so far, is that you have to bring together the experts, the engineering expertise from the application engineers from the real world, from the PLC, the programmers doing the real world PLC, and then in alignment that both parties are really understanding what we are doing together with the programmers from the virtual world. And also very important is that we get in all the knowledge, application knowledge, process knowledge, as Ulf already explained, these knowledge equations we already know from ozone, UV, water matrices, these delta UVT equations. So all this existing knowledge need to be also brought up to the table that we can build up on this information, the modelings. And on some words on principles on modeling approaches, and we will use a wider range of different type of modeling. So you can, on the one end, you have this kind of deterministic or so-called first principle models which are equations, known equations, physical, chemical, biological. And the other part is then these machine learning elements where we will build on artificial neural networks. And we want to combine these model approaches to get as the outcome, as already mentioned, that we develop models at the virtual twin, at the digital twin, which models these process performance on disinfection and can model what is the input from ozone, what is the input from UV, and how to play around with these two treatment steps to get different performances on disinfection, and also understand the impact of disinfection with or without elimination of this chemical of emerging concerns. And the idea is here to get out from all these data as an opportunity to have a virtual sensor to predict disinfection performance of different operational conditions. And just a quick view without going in too much into the detail, but here we have an idea, a setup of a systematic for an artificial neural network, which means this is really mimic these our brain, what's happening in our brain as neural networks. And in general here, we will build up, we started already and will build up these different models with a specific architecture for ozone, filtration, UV. There is then important to set up the right architecture for that model and to think about the right input data for the different steps. And overall, we will have a kind of optimizer, which is a kind of search machine, which is then able to always select the best outcomes and the best solutions from all these variants coming out from all these modeling. And you can see here that is then really important to get a good data set as inputs, that you get a lot of data for different conditions as input, and then the digital twin here can learn over time and can optimize automatically by itself. So having said that, where are we in the project? So the project started in February 21 this year. So far we have the physical plant installed. So far we had all the alignment for the setup from the physical data list, PLCs to with the modeler, with the two expert companies doing the modeling. We are already decided on the setup, hardware and software setup for the digital twin. And now we are in the beginning phase of getting the input data, starting the modeling. But the project will still go till January 24. So there is enough time to get into different rounds and different validation rounds with the digital twin for that concept to understand when we have the different models implemented, understand in the first round how good is that digital twin to use as a decision support system, because probably not everybody likes to run that out straight away to an autonomous operation. So we will learn just using it as a decision support, and the operator has the chance still to decide what to do in the real life plant. And finally, we will want to see if this digital twin is able to run it in an autonomous operation procedure. So coming back to the question, can water reuse benefit from digital twinning? We think clearly yes, but we still need to validate, and we believe we can bring up results in the coming months and years. And before we open the discussion, we would like to acknowledge the support of the German Federal Ministry of Education and Research, the BMBF, because this is a funded project which enables us to do all this great research, and last but not least, all the partners in that project, because without this broad range of different partners, it wouldn't happen. So then coming back to and open the discussion.
Yeah, thank you to both of you. I think that was a great presentation of a cyber-physical system where physical and virtual world merges and meets, and of course optimizes each other in a cycle of data. Looking at our chat function here, please, I just want to remind all of you, put your questions, your comments into the chat function here in this Zoom meeting so they can relate to that and bring those questions up. At the moment, I don't see anything here. Matthias Meyer, I think that's the status at the moment. So of course, I have a lot of questions to you guys. So then I'll kick this off here, the Q&A session. And remembering what Ulf showed us at the beginning here, you know, your cyber-physical system, let me say your physical side is very much focused on the treatment unit. Can you imagine covering a wider system than, you know, only this unit with the system, with the digital twin? Can you do more than focusing on treatment, Ulf?
Yeah, so first of all, you're absolutely right. It's we come from this very much treatment perspective. So that's also what we want to work out, and where also a strong project focus is on to have treatments which can handle both chemical contamination and microbial contamination. But looking on, let's say, future perspectives, currently, let's say we focus on the treatment, and currently we only focus on the post-treatment. One third step could be the company Aquatune is already working on optimizing the biological treatment of wastewater treatment by neural networks. So we could think about having, like, say, a wider scope, having like, okay, what about having like a full digital twin of not only the post-treatment, but also of the full biological treatment. then we are still on the treatment side, let's say. And if we move out of the treatment part, of course, it's a bit more like this. We have seasonal water demand in agriculture in Germany. So it's a bit like the question like, okay, how does our plant via also digital twin can react on the outside? What is the need of water in the farming sector? Basically, was there precipitation? How much precipitation was there in the last days or weeks? Maybe if the water flow in the river, which is nearby, is specifically low, why not increasing the chemical removal above 80%, up to maybe 90%, 95%, going just a bit higher with the ozone application for those seasons where the water flow is specifically low in the river, so we have little dilution. So basically, I think the digital twin could be widened to integrate outside impacts on the water reuse demand and system.
Yeah, thank you. Sounds reasonable. I pick up a question out of the chat, which is, what is the importance of ozone measurement and the correct mass balance of ozone in this project?
Oh yeah, I know from whom this question is coming. And so first of all, it is important to have a good ozone balance. So, but I would say there are several ways how far to go. In our pilot, so we have the in gas and the off gas. So we are not measuring the dissolved ozone because ideally, under no operational circumstance, there's dissolved ozone leaving the system. We could push it like this, but then we have overdosing of ozone. This is something we don't want to have. On the other hand, if we look on actual full-scale implementations, most of them only measure the product ozone, the gas in the product after the ozone generator. So what do you feed in the reactor? And if you have a gas transfer or mass transfer of more than, let's say, 95, 98%, the mass balance is okay. It's not full, but it's reasonably okay to run a full-scale system. But if you don't have off-gas measurement, you sometimes also miss information. You miss information of the status of potential dilution of the water. Suddenly your off-gas goes slightly up. You also miss information maybe of status on your diffusers. If you have scaling on your diffusers, also the off-gas concentration ozone can increase. So it's also an indicator of the status of your equipment.
Yeah, thanks. And you know, you showed this picture of your sensors, right? And the issues you have with cleaning. Now we have online sensors since decades, right? And I remember these problems with maintenance. What are you actually seeing in the market? Have online sensors improved over years? You know, what are you seeing? Because online sensors definitely are an important link into the virtual world, right? Without that, you don't know what's going on. So that's kind of updating your virtual system.
So I hope not to jam one of the suppliers of online water quality probes, let's say, now to jump them directly on their feet. I have a bit, let's say, a provocative word, especially like if you look on things like UVA, and there are a lot of photometric online measurements. They all are kind of a bit different, but to my opinion, they all work fine. But the problem is the cleaning. Sometimes if you have like, okay, you have a super nice sensor, can scan, I don't know, 200 to 800 nanometer wavelengths, but the cleaning device is just poorly designed. So it's really, I think, where we saw bottlenecks was more on the cleaning side, not on the sensor side. Mm-hmm. And sometimes this is difficult to outcompensate this by some internal, let's say, measurements, corrections. Of course, you can do a lot to try to to calculate a bit like, okay, what kind of drift I have. But I think it's worth spending also reasonable effort into the cleaning device itself.
Okay, so that will not be autonomous. That will be always manual. That's what I hear you say.
And no, this should be autonomous as far as possible, because I think for the future, if we look on, well, availability of personnel, and so I think sensors which need manual cleaning each week, they will not survive in the market. There's no way, I should say.
Thanks. Achim, towards your part of the presentation, which was more the digital setup. I mean, you made it quite clear that this is a very comprehensive task, right? And you're pulling together different skills, different skill sets. What kind of professional experts are involved to develop the digital twin? From background, right? From a professional background.
Yeah, thanks for that question. And that is what I mentioned a bit, is one of my observations, because I'm also from the background, not a programmer and not a modeler, but I'm from the background, a chemist. I learned over these 25 years more on the application side, yeah, the equipment, the water treatment systems, and how that works together, and also a bit on the sensor side. And here, I think, yeah, similar with other tasks in that development world, yeah. Here we also have to bring different experts together. And in this specific case, on your question, I think it's the application knowledge that we have to bring these application process engineers together, which understand very good these water chemistry and these treatment processes. That's one part. Then we have the knowledgeable experts, the programmers who are setting up since years these PLCs and SCADA systems for the real wastewater plant. There you will find also a lot of experts with specific knowledge. And then you have on the other side, you have then programmers who have being experts in using these different type of modeling, yeah, which I just raised that up, and I'm also not the expert on that, but between modeling on maybe some easier deterministic equation modeling up to these machine learning modeling. That means for me also that you best is to have a programmer and modelers in the team who has really experience of the whole spectrum and really understands, because probably you can solve everything, or not everything, but maybe programmers think they can solve each of the topics. But here, I think the alignment between the needs and tasks and the understanding of application, physical world, and programming opportunities that you have to find out this, or simplify somehow the things. I think that's important, because before to jump into every detail of each of the programs, it's really, I think, to understand and align on simplifications and to pick on the right stuff and the right model to combine for that specific task. I think that can be only be done if all the parties talk together.
So do I understand you right? I mean, if I would ask who should lead this process if we want to build more digital twins in the water sector, would you recommend a certain profession, or would you more recommend kind of a mindset, a skill, right? Something like this to be successful?
Mm-hmm.
Right. The question is that how does the water sector build up this intelligence, right?
Mm-hmm.
These people to build digital twins, because it's such a powerful means.
And that I would then bring in just an additional party, because we need to bring in then the user, right? That's probably the key, because I started my talk with that. We can do the greatest modeling if the operator or the user, let's say generally the user of the digital twin, doesn't believe in it, doesn't trust in it, doesn't whatever, don't want to use it. So I think that's the other really important part, is that we have to look seriously look at these operators and what are the needs. And to your question, as you ask, how broaden it up, can we include in the digital twin the end user of the reuse water in the agriculture, in the urban irradiation? Can we combine that with rainwater measurements, with groundwater levels, with moisture measurement? So yeah, sure. On the programming side, all that is possible, and the digital twin can do that. But again, I think we really need to ask first then, hey, who is the user? What is really the need?
Right.
What does he know, needs to know, and then bring that in, and then probably I truly believe that we have enough experts in the field to solve most of these needs. But first, we need to understand and define the needs, and then we will find the right model approach for that.
I think we have time for two quick questions, Achim, and the one is coming also from the audience.
Mm-hmm.
You mentioned that you're using the mechanistic models and the AI, the data-driven ones. For the mechanistic ones, what additional process or parameters did you include that are specific to reuse?
These are, for example, these equations or process knowledge we build up, as Ulf, for example, explained, with measuring these online UVA and knowing over the time that there is these equations or relationships between reducing delta UVT through an oxidation process that is related to a degradation of pharmaceuticals. And especially on the other question, how the introduction of ozone, yeah, there's a lot of physical equations available, like mass transfer of ozone gas to water to get the mixture right, to understand the hydraulic retention times of the dissolved water, the reaction zones and the dose, and all this kind of stuff is known and need to be involved and be combined.
Okay, and kind of a wrap-up question to both of you, right? I mean, I think at least the three of us really think that, you know, this kind of water treatment can, of course, benefit from digital twinning. We see that digital twins are prominent and are providing value in other industries where, you know, they are really scaling today. Where do you think is that in the water sector, right? If we just try to copy as much as possible and what is relevant into the water sector, what would you think? How far are we away from this status in the water sector? Is that really scalable, what we are doing, that we can see digital twins more and more coming? And how long did that take? Ulf, what would you guess?
That's a tricky one. Yeah, first, yeah, I think the water sector is maybe a bit behind the industrial sector. I think the question is, it's a bit, I think in industry, there's a clear perspective that it's the clear economic interest is by saving, by optimizing your supply chain, optimizing production. And I think what is maybe sometimes not so clear currently, and therefore maybe there's not so much investment yet, is what's the actual benefit for the utility? Is the utility, is it just cost, or is it just a new status of energy optimization of large infrastructure? Is it also or more reliable, maybe the process combinations? Is it, we just had one project with Berlin Water Company where it was not so much about reducing energy, but reducing the need to manually interfere. Mm-hmm. It's just really say like, okay, we so and so often interfere with our system per year. Okay, let's try to reduce this by a certain number. Also, given the fact that maybe you need to run your plant with only with maybe about 25 or 50% less personnel in 20 or 30 years. So, but I think the clear benefit for the utility is maybe not as clear as an industry. I think that's maybe the main bottleneck.
Okay, thanks. And Achim, a quick question, please. A quick answer.
A quick answer. Yeah, I think most driving factor would be to show up for communicate real cases as much as possible, that everybody can understand in real cases, is there what is the winning factor? And if you can show up that in real cases, that probably other managers, operators will understand and will pick that up if there's that real shown winning factor. If not, yeah, then you don't need it.
So we all think there needs acceleration in that industry, and pilots like this can add, of course, value to this. Thank you very much to both of you for this presentation. Thank you for everybody joining this session. We have a break of 9 minutes, and I think at 5:30 we'll meet again in the main session again. Thank you very much. See you there.